So, hi everyone. First of all, my name is Abrar. Am I audible? Good enough. Okay, so as far as my profession is concerned, I am currently a technical cybersecurity analyst working at a company called TechForce. It's based in Aberdeen. And other than that, I'm also doing my master's in ethical hacking and cybersecurity from Aberdeen. And first of all, I would like to really appreciate you guys that you have specifically taken out your time to be on this track. You could be anywhere, and you gave me that value. Thank you so much for that. And I'll make sure that you do get the value. So today, the topic on which I'm going to discuss and share my insights, that is actually dumb ways to cryptographic failures. In this, what I'm going to do is that I'm going to explain some of the really dumb ways that we do in our real life, and that actually causes different types of cryptographic failures. So let's just get right into it. I'm assuming we have a different set of audience. Everybody would have different sets of expertise and stuff. So for those who don't know, cryptography is basically just a simple science, mathematical science, that we use in our daily life to achieve security principles. These principles include confidentiality, integrity, authentication, availability up to some extent, and authorization, identity access management. Sorry, I'm speaking so much. So yeah, we have very different techniques through which we implement that. We have encryption, we have hashing, we have digital signatures. And not only these, there are so many processes that we have, like key exchange, session maintenance, identity management, access control. Then even talk about the protocols that we have, TLS, transport layer security, IPsec. Talk about emails, we have PGP, pretty good privacy. So lots of things. We use cryptography in our daily life. So what is basically a cryptographic failure then? So cryptographic failure is basically a situation that occurs that when you are trying to achieve a security principle, you don't achieve that. Let's just say you were trying to achieve confidentiality and you couldn't because you were using an outdated algorithm or somewhat like that. So in that case, it's basically a cryptographic failure. So why cryptographic failures are important? There are two things. First of all, the impact. Obviously, let's just say we are trying to achieve confidentiality, and if in case we are not able to achieve it, you can possibly imagine the impact. It's not only informational loss, not only financial loss, but reputational loss as well. And right now, as we speak, you won't be able to feel it unless it happens to you. For any other person, you'll be like, okay, it isn't that much. But when it happens with you, that's where you realize. And the second thing is frequency. These attacks are really common right now. In 2017, it was on third position with the name, I guess, sensitive data exporter. And the 2021 report, it was escalated to the second position named as cryptographic failures. So why do these cryptographic failures occur? So there's one perspective to this. One is that, as you can see, there's a little wizard here and this demon. This demon is basically, you can say, the threat landscape. It's huge. You talk about there are so many different companies working in different sectors. You have energy, you have finance, you have sales, so on and so forth. Everyone is using it. And everyone has different expertise level in technology. Some might be using the latest one. Some might not be using the latest one. And then this one. There are hackers and there are security snoozers. This is the term that I have made myself. So security snoozers are basically those people who are not so good with security. These are the people who are likely to click on a phishing email. I'm not trying to stereotype people here, but generally these two will go hand in hand, and this little thing would simply can't do much about it. So yeah. Then there's another approach. Let's say you are trying to achieve confidentiality, and then again, you chose the wrong weapon. You chose an encryption algorithm that was outdated. Problem. Second one is a little bit more, which I really want to emphasize in this complete project or whatever this presentation is about. As you can see that there are some equations, right? If you see them on an individual level, you will see that the steps that we have calculated, they're exactly right. But we have missed one thing. That is basically the guideline, that you have to follow the BOD-MAS rule, basically. And just because we didn't follow that rule, we are facing an anomaly. Exactly, that's what happens in real life cases. Okay, so now let's just see what are some of the dumb ways through which we achieve those cryptographic failures. So, way one, that's weak encoding. All of the vulnerabilities that I'm listing, I researched them through CWE, which is the common weakness and enumeration library. You can go search on that. Everyone has a number associated with that. So as you can see, this one is a code. Basically what it does is, let's just say you want to store a password in a configuration file. What it's doing is that it's getting the password value from the DB and it's decoding it via base 64. So we know that it was encoded in base 64. That actually is not that good, because as a security researcher, I know it's just a matter of like seconds to convert that back. And if you have something like this at your backend, you are doing wrong. So yeah, it provides that security. It's simply like this, as much as security this grill is providing to this side of the road, it's providing that much. So if you are desiring to achieve confidentiality, what you will do is encoding in base 64 is probably not the best option to do so. Okay, the second one is clear text transmission of sensitive information. Again, we are maintaining a connection with a website and we are doing it through HTTP. And you most probably know that when we are using HTTP, all of the data that we are trying to send or even receive, that goes in clear text. And for anyone who is on the adversarial side of the things can actually sniff that and use that. Now you would be saying to me, yeah, this is so easy, like it's like normal thing. We know that HTTP does this. What's the catch in it? The catch is that most of the people actually don't know. We are from the technical background, that's why we are saying it. If you just go, and these are Google Docs. So if you just put this command on Google, you'll find out the results that are HTTP websites, excluding the one that are HTTPS. You'll see this much results around, I don't know, what's that number? 223 million maybe? Yeah, this much websites are there that are using HTTP. Secondly, there's a tool called curl. We as developers use it much because we have to integrate data between web APIs and send data to APIs sometimes. And what it does is it has this option called HSTS, which is HTTP strict transport security. What it does is that it enforces, even if you type HTTP in the URL, what it does is that it will make the data go and follow HTTPS. But there's a problem in this. What's that? This was a vulnerability that was published in October 26, 2022, that was exploited just because of a single problem. What was that? The thing is that when you are trying to pass it a link, let's say HTTP any website, and you can see this dot right here, right? It's an IDN character. IDN stands for Internationalized Domain Name. These are basically, you can say non-ASCII characters or non-Latin characters that are not ASCII characters. So one hacker just found out that if you can do this, you can bypass this HSTS option. So the main point was trying to tell you that it's not obvious always that if you're using HTTPS, in reality, HTTPS is being used. No, it doesn't really. You have to make sure that you are using HTTPS. So yeah, exactly, that's what I'm trying to say. Then hard-coded keys. Again, so you see that the hash is given here, and the configuration actually checks it against, and if it's right, you're good to go. If it's not, then you're not good to go. Again, a simple thing to do. You can find reversible hashes online, just go paste it, and you'll find it, and it's done. So don't compare credentials with hard-coded hashes always. Reusing nonce value. Okay, so this is kind of an interesting one because nonce basically we use in security in order to get the identity. So let's just say any particular thing you like. Let's just say donuts. You like donuts, and I want to create a family of donuts. And I say that, okay, if you like donuts, be the member of my club. What I do is that I give you a secret number and says, whenever you want to connect with me, just add this number. So I will know that you are a part of my donut club or whatsoever. So the bad thing in this is that you are not changing this nonce value. So let's just say once you have given this secret value to a customer or whatever your client, any attacker, if he has that, he can use it because you're not changing it. So he can impersonate as that person. Another example that I can give is that these lanyards, security just gave you these and they said that we want you to wear them if you want to come to the after party. There's no photo in here. So anybody outside who wants to go there can take my lanyard if he wants. The main thing is that security is not changing these. I know this is just for one time. It's not a good example though. But then again, if you're not changing the nonce, it's a problem. Again, anyone can impersonate that. And for a fun fact, nonce stands for number used only once. So that doesn't really make sense if I'm using it again and again. But then again, I said these are dumb ways, and these are actually followed in real life. That's why I'm talking much about it. So using key post-expiry. Again, if you're checking the validity of SSL certificates. So let's just say I met with a student. He's from Abate, and I want to validate that if he's really a valid student. So what he's going to do, he's going to give me his ID card. Now, because he's a genuine student, his ID card is valid, but let's just say it was expired 2 years ago. Like he graduated 2 years ago. This does not give me, you see there's a gap in this. I need to check the validity as far as the expiry date as well. So yeah, exactly that's what happens. If an SSL certificate is expired, an attacker can interlude in, basically this attack is called SSL stripping. So what it does is that the attacker basically intercepts the SSL TLS handshake process and then presents a fake SSL certificate and then creates an established connection with victim. Basically a man-in-the-middle attack. So yeah. So always check the validity plus the expiry date of the certificate if you are doing that. Weak encryption. I think I've talked about it much. So yeah, basically the same idea. Don't use anything that's outdated such as classical ciphers, low key size, using DES or XOR encryption. Don't just do that. Because brute force attacks are common, confidentiality breached. And this is a key takeaway, that always use those that has good randomness, first of all. And this is a big concept. I'm going to explain it a little further as well. And then we have the key size as well, that the key size should be strong enough. So, and then this one is strong non-linearity. So non-linearity is in terms of S boxes. S box, as you know, stands for substitution boxes. We see those in block ciphers. Let's just say AES, DES. In that we use these. And there's a proper concept. It's not just like we are making randomized S boxes. It doesn't really happen that way. Okay. So key exchange without authentication. So this one is just a normal example that I've created. Let's say there are two parties, A and B. They want to exchange a key, a shared key. How they actually do that? They do it by this way. They have a generator called G and they have B. What they do is that they'll calculate these values. Let's say this B is a random number chosen by B, and this A is basically a random number chosen by A. What they do is that they'll calculate these publics and then they will share it with each other. And then again, they'll do the same step and they will reach a shared key. Let's discuss it in terms of an attacker. Again, if you can see here, the attacker, because it's not being authenticated, what he will do is that he will generate a fake key of Y from Y side. I'm sorry I labeled these as XFY. This doesn't really sounds good because in maths it boggles my mind also. But yeah, the same concept. What he will do is that he will just distribute these values and maintain two different connections with A and B, considering and making them feel like they are talking to each other when in reality they are actually not. So yeah, exactly the same thing. So always when you are exchanging any key, it's a key element that you need to authenticate the other party. Incorrect usage of seeds in pseudo-random number generator. So you can see this is a piece of code, and I have used this function called rand. So what this does is that it produces random numbers according to an initial generator, which is here, srand1. So when this is fixed, what it will do is that it will always generate the same random values. So just like this. So if I have this piece of code right here, no matter how many times I run this, I'll always get these values. So obviously these are not random. There's a pattern to it. And when there's a pattern to it, obviously that doesn't provide good security. So for security, a true random number generator should be used. And then we have use of RSA without OAP. So RSA, as you know, is an asymmetric algorithm basically that you use. Here is just a normal exercise that I have made for you people. So you can see there's a modulus called M, then there's a public key E, and then there are two messages, M and M1, and I have encrypted them using the RSA. So cipher is equals to message raised to the power public key and modulus. Yep. So we have these two ciphers. Can you actually tell identify any pattern between these? Any? Kind of look similar. right? So the first one tells me that actually that these two ciphers contains exactly the same word. That's one of the key things that I can identify from this. And then there's another one as well. What's the other one? The other one is that the same word is being encrypted twice in a same sentence. How do I find this? So here, if you can see, these were two words, hello world and hello hello. So I encrypted them. Yeah, I know some of you might be thinking, you didn't encrypt them. What you did was, this public key is 1. When this is 1, obviously the message is going to be less than modulus. But this was just to kind of give you a context that it happens in this way. Obviously, if I used large values for RSA, let's just say 1024 bits, obviously it would take a little more time. But then again, the idea is that RSA is deterministic. So you need to have a way to figure it out. So yeah, those folks that were giving me a look saying he doesn't do that, he didn't do that, what he's trying to say. So yeah. So use optical asymmetric encryption padding always with RSA. If you're using RSA, though what I recommend, I'm not a security guru or someone, but generally for encryption, asymmetric ciphers are not that good. They are used for digital signatures or authentication kind of stuff. If you want confidentiality, you can use AES or ECC, elliptical curve cryptography for this. And these are just general RSA issues, like there's a common modulus attack. And what you need is that sometimes you don't even need the private key in order to get the main message out of it. And then this one is chosen ciphertext. This one is kind of my favorite because you see, let's say you're an attacker and you get a ciphertext. What you do with it is you multiply it with a number called, let's say, 3, and you send that to the receiver. Now, obviously, when the receiver will try to decrypt that number, he will not get the right number because you fabricated it. So then you can go to the receiver and say, oh, I'm really sorry. I didn't know you got the wrong number. Can you send it back to me? And I can have a look. I don't know, maybe these guys make what kind of protocols. And once you get that decrypted number back, you just need to divide that with what you multiplied it, and you'll get the original decrypted number without actually having the private key of that person. Then again, the whole security of RSA actually depends on this modulus. Where is it? Yeah. If you are able to break it into 2 prime factors, P and Q, generally you can make your own public or private key, and then you can do whatever you want. So yeah, basically, this is the whole summary of it. So always choose the right weapon. Know how to utilize your weapon to max. There are problems in you need to make sure that you use the right amount of security required and have a holistic view of security. Because when we are talking about, let's say, confidentiality, I've only talked about RSA. There are so many other things you can look forward to. But just make sure that you have in-depth knowledge of it, and you don't do something like I discussed earlier, where I said that you need to follow the BODMAS rule, right? You are just missing the BODMAS rule, and for that you found that anomaly or whatever. So yeah, that's it. Thank you so much. If you have any questions.